Okay, so hello everyone. My name is. We will continue with with the differentiation and integration. Now today we will see some application of those, and today we will mostly use the inbuilt command in Matlab. Okay, so today I will first start with code, then I will go to the theory part. Okay, so let me share my screen. All right. So yeah, I hope it is visible to you. So today first we will see some application of. So first so so first suppose let's define the function. So first let me show you the symbolic computation here. Okay, then we'll go to find the derivative of some numerical data point. So suppose the function is exp of minus x square times sine of x. Okay, so let's plot the function. So to do the plotting of any symbolic function, we need to use f plot. Okay, so f plot, and I need to provide the range. So suppose 0 to 3. Okay, so let me just run it. Okay, so plus 11. Just a moment. Okay, and you can see now we need to find its derivative. Okay, so I can comment it out because we don't actually need to see the function. Control R for commenting out this. Okay, of any function, any symbolic function is MATLAB. The command is diff. Okay, so suppose uh, g equal to diff of f. Now if you just run it, it will give you the functional form of the program. E to the power minus x square cosine of x minus 2x e to the power minus x square sine x. Okay. Now, if we suppose want to plot this again, we need to use the f plot. So maybe I can do this function, then hold on, and f plot d 0 3 is the blue one is the the plot of the original. Now suppose you do not have, you have some data points and you need to find its z naught. Okay, so let us do the test here. So okay, let me, so my symbolic variable is x to 0.001 to 3. Suppose if g, now suppose this is h. Okay, h equal to exp minus z dot square, because z is a vector, dot star sine of z. Okay, now it will give me a function, right? Now, now I want to find the symbolic derivative of this. Okay, that means so my function in terms of z, I need to find dh dz, and for that we have an inbuilt command in MATLAB that is called gradient. Okay, now I will go into detail our gradient in a moment. But first, let the result will be dh dz. Okay. Now, if gh, suppose my derivative is gg of h divided by. So this I did with dz, and here this is my dz, that is 0.01. Okay. So that is 0.01 divided by. Okay. Now, to verify it, what I can do, now you can see that it is already under hold on. So I just need to plot this function against z, plot z gg, and suppose I so maybe the color will be magenta and dash dash. Okay, now let's check if this is working or not. Yeah, so you can see that this blue one is the original curve. Okay, this just a moment. There is a connection error. It will be fine in just 1 minute. Just hold on. Okay, so you can see that there is a magenta dashed line, and behind it there is a blue solid line. Okay, I think you can see this. So I am, so let me just increase the line width maybe made 8. Oh no, so I increase the size of the other thing. Just a moment. Uh, okay, so for if plot, this is I cannot increase line width like this, but you can see that behind this dashed magenta line there is a faint red line. So this faint red line is coming from the symbolic computation of this derivative, this diff. Okay, and I have plotted it. And this magenta line, this magenta dashed line, it comes from this inbuilt use of this gradient. Okay, so it is coming from here. Remember, the gradient of h indicates dh. Okay, and I am dividing it by 0.01. That means 0.01 is dz here. So yeah, so now as a whole it is giving me dh by dz. Okay, and I am plotting it, and it is giving me this answer. Now I hope the idea about diff is clear. Now let me talk you about the gradient thing. Okay, you know so for that, I will take another example. Right. So we know that for any particle, for any particle under some acceleration, that its displacement is x equal to some u times t plus half into acceleration into time square. If my initial position, if I assume my initial position to be 0. Okay. So let's do that. So here my time will vary. Time may be 0 to dt. Okay, so no, first let me just give you a brief. First, let me talk about the gradient. Then I can go with this example. Suppose you have some data point. Okay, so x equal to 23, 37, 55, 45, 62, 89, 78, so on. Now, if I write gradient of x, what will it mean? Gradient of x. Let's just verify that. Yeah. So see, what is gradient of x? So the first number is 14, then 16, 4, 3.5, 22, 8, and minus 11. How are we getting that? Remember that when I am just using gradient of x, it is just finding difference between 2 points, subtraction. Okay. Now it will subtract second point to the next point to the previous point. Now suppose, now see that the size of x is 1 2 3 4 5 6 7 7. This is a 1 cross 7 vector, and also for the gradient of x the size is 1 2 3 4 5 6 7. Its size is 7. Now it is finding difference between 2 points. Now for the first point, okay, its next point is 37. So it is finding 37 minus 23 is 14. Now for the second point, so this is, we know that this is just a forward difference technique, 37 minus 23. Now for the second point, 37. Now it's for this point, it is calculating in the central difference method. Okay, 55 minus 23. 55 minus 23 is 32 divided by 2. Now when I am not dividing it with something dt or dz, it will assume that it is divided by 1. Okay, this is how the gradient command is built. So for the second point, it is calculating 55 minus 23 divided by 2 into 1, because it will assume that the h equal to 1 when nothing is specified. Now for this third point, it will do 45 minus 37, that is 45 minus 37 is 8 divided by 2, that is 4. For this fourth point, it will do 62 minus 55, that is 7 divided by 2, that will be 3.5. Now for this point, fifth point, 89 minus 45, 44, again divided by 2, 22. Now for the last point, okay, for the last point, it will simply do the backward difference technique. It will just move one behind. 78 minus 89, it will give you minus 11. So for this first point and this last point, okay, its accuracy is of order h. But for the intermediate point, its accuracy is of order h square. So while using this gradient, you need to keep that in mind. So we will see. I will show you an example where you will see that it will affect your calculation. Okay, so let's see that. Now here I am assuming. So again, let's go back to that particle example. So it's 0 to 0.01, no, maybe 0.1 to 2. Okay. Now suppose its initial velocity is 3. Now its position x is equal to, okay, so I have to mention the acceleration, maybe acceleration equal to 10. Okay. So its position at any point, it will be u times t plus 0.5 times p dot square. Okay, it will be its position at any instant. Now if I find its derivative, it will give me the velocity. So v equal to, now v equal to gradient of x divided by 0.1. Why 0.1? Because this is 0.1 is dt, so its dt is 0.1. Okay. Now if I again find the derivative of v dv dt, it will give me acceleration, and we know that acceleration should be 10. Okay, so let's verify that. So acceleration, maybe this is f equal to gradient of v divided by 0.1. So in principle, it should give me a constant acceleration at all the time. Okay, because this is how the problem is built. Now let us plot all of this. Plot x, sorry, t comma x, hold on, plot t comma b. So I will not write the legend or access all those things. Those things you can do it yourself. And t comma f. Okay, now let's see this. Ha. So you can see that this is the plot of x versus t. Okay, this blue straight line. So it is not actually straight line. It will be a parabola, because here I have only a few data points. So it looks like a straight line. Okay, but it will be actually parabola. Okay, if you increase your time step or the time range, it will be a parabola. This orange one is the straight line. Okay, and this yellow one, it is the acceleration, but it does some funny things at the beginning and at the end. Suppose I am at some intermediate points. It is showing one. Just a moment. Huh? Just a moment. It should be 10. Aha. I forgot to multiply this 0.5 into a. Yeah, it is more prominent. Now see that this axis. Yeah. Now it looks like a parabola, right? This blue one, it looks like a parabola. This looks like a straight line, but here there are some bend. I don't know if you can see that, but it is very prominent for this acceleration curve. This yellow one is the acceleration curve. Now here you can see that it is giving me correct acceleration at the intermediate point 0.4. It is showing 10. Okay, let me show you. Yeah, at 0.4 it is showing 10. Okay, but at some distant point at 1.3 time 1.3 it is showing the acceleration 10. It should be the answer, it should be the correct answer. But at the initial point, you can see that at the initial point the acceleration is not actually 10, because at the initial point also the same things happen at the final point. It is acceleration is not 10, because what I have told that at the initial at the starting and at the beginning, sorry, at the starting and at the ending, this gradient has some error. The order of error is order h. Okay, but for the intermediate point it use central difference scheme, and its error is of order h square. Okay, so it is more accurate, and it is giving you the correct answer. But for the initial points and the last point, it is showing you it will give you the error. Similarly, the same thing happens here. This velocity should be a straight line, but you can see that at the end and at the starting, it is not behaving as a straight line. Okay, but for the intermediate point, it is acting like a straight line. Okay, so you need to keep that in mind while using this scheme. Now suppose what will happen if we use diff? will it does it have some kind of problem, or it is works perfectly? So let's test that. For the same problem, here I cannot here this t here, let me just erase all of this. Here my I need to mention a symbolic variable, then that will be t. Okay, so here x, I need to again mention u and a, and x will be equal to u times t plus 0.5 into a into t square. Okay, this is x, and the v will be if of x. Okay, here t is the only symbolic function, so it will automatically assume that it will differentiate with respect to t. You don't need to mention it, and a equal to if, sorry, not a, maybe let me write as if equal to if of t. Okay, so this v is the derivative of with respect to t of x, and f is the acceleration, that is dv dt. Now I can plot this. If plot x, and the time should be 0 to, sorry, 0 to 3. Hold on. So let's test it. Right. So you can see that these are not very thick line. Okay. Let me increase the thickness, maybe 6. Right. So this blue one is the position curve, so there is no problem, and you can see that here this diff works perfectly. There is no deviation from the straight line for this velocity curve, and no deviation from this constant straight line parallel to x-axis for this acceleration curve. It is 10 everywhere. At the end, it is 10. At the beginning, it is 10. Okay, unlike the gradient. Okay, but most of the time you need to work with this data point. Okay, not the same, most of the time you will not have this functional form. So then you need to use gradient, and you need to take care of the error. Okay, so so it concludes our discussion on the so it concludes our discussion on this finding derivative using MATLAB command. Now I can talk about the integration. Okay, now for integration, I will use three techniques. Okay, one is int. Int is it will be applied for the symbolic computation. Okay, uh, then I will use integral. Integral is applied for data points, but if integral does the numerical integration, but it is applied for any kind of function. Okay, as well as the data, as well as you can convert a function to data point, and you can do it. Uh, but the int works on only those functions whose integration can be found analytically. So it does the analytical integration, not the numerical integration. And then I will use trapz. Trapz works on the only the data points. Okay, if you have data points, then you have no other options to use a trapz. Okay, so I will go very slowly on one by one. So first, let me talk about int. Okay, int is for analytical computation of some functions. Okay, so let's first I will do some simple examples, then I will show some serious applications of this integral, trap z, of those things. Okay, these things are very useful. Okay, so the maybe the function is f equal to xp minus p square star, same function. Okay, let's see if it is integrable or not. The result will be res equal to int f, and I need to specify. So remember, so here, so okay, so let's just do int of f. No, first let me take a simple example. Okay, maybe sine of t, and just do int of f. So just int of f is giving you the indefinite, so the result of the indefinite integration result. Okay, now if I add limit, maybe the lower limit is 0, upper limit is 2 times pi. Now let's see what will be the result. So it is giving me the result is 0. Now I multiply it with the exp of minus p square, and let me us remove the limit. Let's check if it can give any answer. Yeah. So you can see it gives me back the same thing. That means the indefinite integration for this function is not possible. At least Matlab cannot do it. Now if I provide a limit, maybe one limit is 0, another limit is inf, infinite. Inf means infinity. You can write, so infinity will give you some very large number, and you can write it for the symbolic integration. Okay. And yeah, and it is giving you some result. This pi to the power 1 by 2 ERF is the error function, some complicated expression. Now what is the value of this? Okay, now to do that you need to use double. So this is a symbolic expression, right? Exp to the power minus 1 for ERF something. So to get a number from it, you need to use double. double. Double is a type of the double is a data type. Okay, it converts a symbol to any number. So and it gives you this answer, 0.4244. Okay, so I hope the idea of using int is clear. Now let me show you for the same example. Let me show you how to use the numerical integration. Okay, so for the numerical integration, so suppose if equal to, for the same function, I will take the same function, exactly the same function. So remember this answer, this is 0.4244 using the analytical expression. So f equal to @x sine x dot star exp minus x. No, maybe not like this. Okay, so the first let me just do this. That's okay. Now RE is equal to integral f 0 inf. Let's check it. Yeah, you can see that the numerical integration also is giving you exactly the same answer. Okay, now if I just write integral, so integral, whenever you are writing integral, suppose you are giving integral, okay, and you are not giving anything, it's just integral of f, it will show you error. because this integral is just built for the numerical integration. If you don't specify the upper limit and lower limit, it cannot work. Okay, so you need to specify the limit here. Now, so it does. So it does. It can do. So it does the numerical integration for a function. Okay, here for a function. Now, suppose I do not have a function. I have some data points. Okay, so how can I build? How can I generate data points for this function? That is very easy. So a let me define a vector. So 0.0 to 0.1 to, so previously it was infinity. Here I cannot write infinity, maybe 50. 50 is a quite a large number. Okay, so this is the vector which is going from zero. Okay, so first let me take a large step size, maybe 3. Let's see. And my f equal to exp of minus, here x is a vector, x dot square. So in the last example, writing dot was not necessary. Okay, because that x is just a variable, and I am defining a function. But here, if x is a vector, so okay, so writing dot square dot star is necessary here. So this is my function. This is the expression of a function. Now I need to find the integration. Now I need to, so here I do not have any functional form here. If you just run it, then if is the, you can see that I think they're one into, so let me increase the size. Here f is 1 into 17 double and x is 1 into 17 double, so both are just data points. Now I need to use symbolic integration. Sorry, I need to, so I need to use trap z. Result equal to trap z x comma f. Let's see what is the answer. Okay, it is giving me some wrong answer, so let me try over again. So let's 0 to 250. Yeah, so 0 to 0, 0 to 1 to 50. Yeah, so you can see that it is closing 0 to 0.5. So the correct answer was 0.4424, right? If I do 0.1, 0.4246, maybe 0.01, 4244, 0.005, 4244. So it converts. So it is converged. Okay. So here this is the, so here you can, while you have a data point, still you can find the integration of it using this trap z command. Okay, so trap z is just the simple trapezoidal integration. This is inbuilt in Matlab, and you can use it, but you need to very careful for the data point you are using, for the step size you are using. Where here the step size is 2, and you can see the answer is nowhere close to the actual answer. But if you use data size equal to 0.01, then if you reduce the data size, it is giving you the correct answer. So you need to be careful about this. Okay, so using trap z or trap z, integral, and int, we can get the same kind of answer. But integral and trap z will be more useful compared to this int, because many functions will not have any analytical expression. Okay, let me show you one. uh, I can work with the same example, I suppose, but not like this. Suppose SYM symbol x int f01. Yeah. Oh, sorry. I need to verify. I need to write. Yeah. So you can see that it is giving you that exactly the same thing you have written. Okay, that means that it doesn't have any analytical solution for this range. Okay, just give me 1 minute, I'll be back, then I will show that for using trap z and the integral I can find the answer for this. Okay, just give me a moment. So now I will show that using integral and trap z, I can find the result of this integration for this defined limit. Okay. Now let me erase it. Here f equal to x. One thing I can do. So let's pick. Um, okay. So here I need to use the dot. Okay. Right. So yeah, so I told it wrong. So for the functional form also you need to use this as a dot. Okay, as a dot square and dot star. Okay, the you do not need to do it for the symbolic computation. So here for this trap z, sorry, for using integral, the that result is 0.2947. Okay, and the time required is 0.043889. Okay, this for this code. Now for data point, okay, so let me use the data point. So 0 to it goes again, just a moment, huh? Now for trap z, Let me first define the limit as 0.1 to 1.0. Remember that the answer is 0.2947. Assume this is the correct answer because we do not have any analytical reference, but assume that this is correct. Okay, Matlab is giving this answer, so it will be correct. Okay, so now define your limit like this, and suppose this is your vector f exp of minus x dot square dot star sine of x. Now here you need to use trap z, trap z, x comma f. Okay, and see, let's see the answer. 0.2935. Okay, it is not 0.2947, and the time required is less. Okay, previously it is 0.04, now it is 0.018. Now, so I need to increase this 0.05 maybe. Time required is this, and 0.01. Yeah, now it is giving me the answer 0.2947. Okay, so you can see that here I have used this peak and talk just to show you the how much time is required for both of the methods. But you will see that this the time required is completely on the it will vary from problem to problem. Okay, most of many cases you will find that TrapZ is giving you the faster answer, and other cases you will find that the integral is giving you the correct answer. Sorry, the faster answer. Okay, okay. Now, so we have learned some basic of the integration in Matlab. Okay, now I will show you some application of it. Okay, let me stop share the screen for now. I will again come back. Let me share my screen from my tab. So suppose you have some data signal. Okay, 1 second. Yeah. Suppose you have some data signal like this. Okay, suppose this is your if not by if some t. You have now you are told now you are told to find a frequency. So how to do that? So one application is the Fourier transform. So let me tell you in bit detail. Suppose you have a function like f of x equal to some a of sine 3x plus b of sine 5x plus c of sine maybe 10x. Okay, so if so you can try. I will show you in a moment, but you will see that the combination of this sinusoidal mode will give you something arbitrary like this. Okay, some arbitrary, it will seem like a chaotic signal. Now suppose you need to decode what frequencies are present in the signal. Okay, then you need to use Fourier transform. This is a tool that actually uses integration to give you that the one frequency is 3, another is 5, another is 10. It will give you back this answer. Okay, and the formula for that is the Fourier transform f of x, f tilde of k. F tilde is the Fourier transform of fx, that is 1 by square root 2 pi minus infinity to infinity e to the power minus I k x f of x dx. Okay, it will give you this signal that 3 is present, 5 is present, and 10 is present. Now suppose you have decoded the signal. Now if you again want to get back the original signal, okay, then you need, this is the Fourier transform, then you need to use the inverse of this Fourier transform. That is, from f tilde, suppose you have this f tilde of k and you need to get back this f of x, then you just need to do f of x equal to 1 by square root of 2 pi minus infinity to infinity e to the power I k x f tilde of k dk. Okay, so see what is, I mean, this definition is not my concern for this class. The main thing is the using of this integration. Either you can have a functional form or you can have some data point. That means you can use integral or trapez. Okay, you can use both to get back this answer. Now let me show you an example of this. Okay, first I will show an example for this, a combination of the sinusoidal signal. You will get back this answer, and then I will show you for any random signal. You can generate random number in Matlab. Okay, for such a random signal, I will show you that you can exactly decode decode the frequency, and finally for using the inverse Fourier transform you can get back this f of x. Okay, you can get the actual signal back. Okay, so this is actually very powerful tool. It is also used in photo processing and many other things. Okay, I will just show you a basic application of that. Just a moment. Let me share my screen from my computer. Right. Just- Okay. So let me tell you what I have done in the code. So here first I have provided a range. Okay, so let me just do it clearly. Okay, then it will be clear for you. Hmm? Here you will see that I have used both functions and integral and the trapez. Okay, let me just do it. I can tell it from here. Okay, I am telling it from here. Okay, so here I have defined, this is the range of x. Okay, the x is varying from minus 2 pi to 0.01. This is my step size. It will go up to 2 pi. Okay, this is y1. So here instead of sine I am use cosine function, but both of them will give me the same answer. So I mean similar answer. answer. So y1 is 0.2 cos of 5x, y2 is 0.5 cos of 8x, and y3 is 1.3 cos of 10x. And y is the summation of these three. And first let me just plot this thing. Okay, plot x comma y. Okay, let me give a breakpoint over here. Change folder. Yeah, so you can see this is not very this is not very simple signal, a complicated signal you can see, but it is periodic. Here this point, this point, this point, they are repeating. Okay, so my main agenda is I need to get back this 5, 8, and 10 from using Fourier transform. So let's do that. So I don't require this plot, this y at this moment. Okay, okay. So remember that uh, in the derivation, in the formula, I had, so the what was the formula? It was e to the power minus integration minus infinity to plus infinity, e to the power minus I kx fx into dx. Okay, so this was the formula. So so I need to vary the k as well. So minus 15 to 0.1 to 15, because for the inverse Fourier transform I had dk. Okay, so I need a range of k as well. So here this fk I have predefined. This fk I have defined, this is related to f tilde of k, and f tilde of k will have the length of k. Okay, okay. Now for I equal to 1 to length of k. Okay, this I have defined the function. See the 0.52 cos of 5z, 0.58z plus 1.3 this into exp e to the power minus iz into k. Okay, that means for a single, so for a single k I should have one, I should have one value in the Fourier plane. Okay, because for I have taken various k, and for each of the k this Fourier transform will be valid. So I have done that. So that's why I have used a loop over here. Now what is the fk of L? 1 by square root of 2 pi, this is coming from the formula, into integral function 1 minus 50 to 50. You can change this as you wish. So this is corresponding to minus infinity to infinity. I have tested that for this limit it is giving me correct answer. Okay, you can increase the limit if you want. That is not a problem. And in, so after that it will give me a signal. Now what I have claimed that it will give me back this 2, 5, 5, 8, and 10. So let's check if it is working or not. So yeah, so right, so one signal, this is as 5, another signal. So you can see there are some new, these are this small, this peak. Okay, the one peak is at 5, another peak is at 8, and another peak is at 10. So the theory is working. Okay, now after that I need to get back my original function and compare with the initial function. The initial function is the y, and from this f tilde, this fk, I will get back fx using the Fourier transform. Okay, so I have done it over here. So this is here I am using trap z. Okay, because why I am using trap z? Because I do not have any functional form of fk. I only have fk as data point, and when I have data point I cannot use integral, I need to use trap z. So I have exactly done that thing. Okay, the idea is the same. I am just using integration, and for a single value of x I need to have a point on the xy plane. That's why I am using it inside a loop. For ll is my identity, is the indicating the loop. Okay, and I am doing the integration with respect to k. You can see that k comma fk e to the power I k x of ll. That means for each value of x I need to have value on the xy plane. Okay, and finally I have plotted. So this is my the result after inverse Fourier transform, and this is my original plot. Okay, now let's see if it is working. Okay, okay, just a moment. My connection, there is a it is a connection failure. Just a moment. Just a moment. Right. So, so let's just now try it. Okay, let's run the code. This I have already shown. Yeah, now this is the plot. Now here this blue one is from the original curve, that is the y, okay, which is y1 plus y2 plus y3, and this red dash line is from the inverse Fourier transform. Okay, and you can see that this is working perfectly. Okay, so I will share the code with you and you can play. So remember two things. Okay, always keep in mind, you need to, so from problem to problem you need to change this thing 0.01. It may not be, it is giving me correct answer for this problem. For some other problem, it you may need to increase or decrease the step size. The same thing happens for the this 0.1, this dk as well. You need to increase or decrease the step size. Okay, I am mentioning that you may need to increase the step size, because if you take very small step size, sometimes it can give you the numerical error. Okay, so just I will share you the code. You can play with it. Okay. Now, so this is for any sinusoidal signal. Now, suppose you have a random signal. Okay, then what will happen? So here, previously I had a functional form of the cosine x, so summation of cosine x. Okay. Now I do not have any functional form. So here I just have liberty to use tab z. I cannot use anything else over here. Okay, so what I have done, so this is my limit of x. Okay, and this is the y. Okay, so I have changed it in this way because I needed everything, I wanted everything in the column, as a column vector, so I have just changed it, x equal to x prime, and this is the limit of my k. Okay, we see that here dx is 0.2 and here dk is 0.0005. Okay, now, right, now remember that remember the original formula. Okay, the original formula was, okay, just so, okay, before doing anything, let me just run it and see if it is working, then I will continue. It is working fine. So now remember the original formula. The limit was minus infinity to infinity. Okay, now my original value is from minus 5 to 5. Okay, so I wanted a larger value of x. Okay, larger set of data points, but I do not have that. So in order to do that, I have used extrapolation. I have already told the use of entropy one in the while discussing about the interpolation. Here I am using this command extra p. Okay, this is the extrapolation, so it will fit your data accordingly. Okay, now I will work with x1 and y1. Hmm? So here I am using trap z and integrating with respect to x1. Okay, yeah, and then uh, and this is the forward Fourier transform, and it will, this thing, this will give me the signal that is present. Okay, so let's just check the signal. Yeah, so it is the signal. You can see that there are many oscillation, and the peak appears at x equal to 0.006. This is the highest peak, but there are many other peaks, local peaks that is present for this random signal. Okay, right. Now, after that, I am doing the inverse Fourier transform. Okay, for with respect to x, because I need to compare my value with respect to x, not with respect to x1. I just needed x1 for the integration, for the definition purpose, because I want the limit to be minus infinity to infinity. That means a large number. 5 is not a large number, but I have tested the 30. For 30 it works fine, but I need my original result back with respect to x. So here I have used the simple limit x. Okay, see that this is not x1, this is just x. And finally I have compared the result. Okay, let's see the comparison. Yeah. So you can see that original blue curve. This original blue curve is the random signal. You can see that this is completely a random signal. Random data points are present, and this red dashed line, sorry, I mean this blue dashed curve are the original, and this red solid line, this is the we are getting from the Fourier transform, inverse Fourier transform. You can see the result is quite satisfactory. There is some difference. I need to I need to increase the, say, I need to increase the dx or dk somehow, or I need to modify it. After that we'll get an exact comparatively better answer, but you can see that the result is quite satisfactory over here. Okay, so I will share you both the codes and you can play with this. Okay, so I will show you another application of this integration process. That is the, this is the Fourier transform, and that will be the Hankel transform. So let me share my tab screen once again. Right. Okay. So now this Fourier transform, this is applicable for the Cartesian coordinate. Okay. XY coordinate, XYZ coordinate. Now this Hankel transform thing, this is applicable on the cylindrical coordinate. The idea is same. You have some data point. Okay, so you have some signal in this plane in the radial coordinate, and you need to get back. Okay, so so for the cosine or sine in Cartesian will be Jn. Jn is the Bessel function of first order, Bessel function of the first kind of nth order. Okay, so you have some J0 of something. It will be oscillatory function like this, but it will be decaying. Okay, this is J0. This is corresponding to sine or cosine in the Cartesian coordinate. So you have some function like J0 K1 R plus some A J0 K1 R plus B J0 K2 R plus dot dot something like that. So using Hankel transform, I will get back this answer. Okay, and similarly, like the inverse Fourier transform, there is inverse Hankel transform. So finally, I will get back this answer as well. Okay, so let's go to the definition again. F tilde of k equal to 0 to infinity. Okay, not minus infinity to infinity. R J0 of k R f of r dr, and to get back fr it will be 0 to infinity k J0 of k R f tilde of k dk. So this will be the result. Okay, so I will quickly show you two examples, then I will go to solve some theory problems. Okay, because so the next class is on Sunday. So in the next class I will mostly show you many codes. Okay, because that is the last class. So I will show you that Matlab has some robust tool to do the ordinary differential equation, the partial ordinary differential equation solving tool. So I will show you extensively how to use those things. Okay. Okay. So um, yeah, let me share my screen. Just a minute. So I have stopped sharing. Now let me. Okay, so let me share my Matlab code once again. Okay, now it is. Just a minute. Just a minute. Share it again. Okay, so let me show you one example. Right. So here this is the range of R. Okay, 0 to 0.01 to 25. Okay, and this is my function 0.3 Bessel J. These are the root of J0. Okay, Bessel J0. You don't need to get into a definition, but the idea is I should get back signal at this point. Okay, so and this is my K. Now, so if I plot R and F, let me just check. So this is how the function will look like. Okay, the combination of J zeros. Okay, now so here I am using doing the Hankel forward Hankel transform. Okay, so for each one k in the I should get back one f tilde of k in the k plane. See, this h eta is the f tilde f k, right? And again using this I am getting back my answer. Okay, so this is the forward Hankel transform. This idea is just same like the Fourier transform, so I will not go over it again. You can just remember that the limit will be different. That it is not minus infinity to infinity; it is 0 to infinity. So you need to modify your k and r accordingly. Okay. So let's check. So this is my original plot R and F, and here this is coming from the inverse Hankel transform R and eta, huh? And here I have plotted K, H, and eta. Okay, that means this is the K versus the F tilde of K. That means the signal in the K plane. In the K plane, I should get back the frequency. Okay, first check this answer. So one signal should be around 2.4048. So this is 2.4. Okay, another will be 5 point something, so it is at 5.53. Another should be close to at 8.66. Okay, so the Hankel transform is working perfectly. It is at 2.4 something, 2.4. It is at 5.56, 5.4, and it is at it is at 8.66. Okay, So here it is 2.4, it's 5.54, close to that, and it is 8.66. Okay, and you can see that this is the comparison. This this red dashed line, it is from the inverse Hankel transform, and this blue solid line is from the original function. You can see they are overlapping on top of each other exactly. So the code is working. Okay. Now I will show you one last example from this Hankel transform. So let me, what will be the example? So this is one example. So what I have done here, this is, now I have changed the definition of summation of Bessel function. Now I have e to the power minus r square. Okay, this is a Gaussian function, and for a Gaussian function, its Hankel transform is also a Gaussian function. Okay, it will be some e to the power minus k square by 4. I'm not, something like that. Okay. Similarly, in the Cartesian coordinate, the Fourier transform by some constant. Okay. Just a moment. So give me just 2 minutes. I'll be back in a moment. Okay. So so here I have defined a function e to the power minus z square. So it is r times e to the power minus r square times Bessel j0 ki times r. Okay. So it is the loop inside k. For each k, I need to find a value in the k domain, and here integral 0 to 5, because here 5 will work sufficiently good as infinity, because if you put e to the power minus 5 square, that is e to the power minus 2 to 25, it is 0. Okay, this 5 comes from that fact. And here again I have, sorry, right. So and here, oh, okay. Huh. So here for this I am using, here I have already the value of this h eta, that means fk, and here I am doing the inverse Hankel transform. Okay, now let's see the final answer. I will share you the code. This is exactly similar to the last problem. Okay, I just want to show you the results. Yeah. So originally I had a Gaussian, that is a blue solid line, and this red dashed line is from the inverse Hankel transform. So they are overlapping on top of each other. Okay, and this one This one is from the Hankel transform of the Gaussian. Like I have told that it will be again a Gaussian function. You can see that this function is exactly a Gaussian. Okay, but you can see that the range are not same. This its maximum value is zero near 0.5 and its maximum value is 1. Okay, so there is a little bit difference. So, but essentially qualitatively this is a Gaussian function. Okay, so I will stop here. So that's all for the coding part today. Now I can go. So now I will solve some theoretical problem for the regarding the differential equation. Okay, so I can stop sharing. Okay, now let me share my screen on tab. Okay. Let me download the file. Okay. So I will solve some theoretical problem today. Again in the next class, that is the day after tomorrow, Sunday. There also I will solve some theoretical problem, but mostly I'm interested in showing you the some tool in Matlab which you can use to solve differential equation very easily, and this is a very robust tool. So okay, so yeah, so here this question says that first order Alan Bashford technique is that there are four options. So this is an explicit. This is an explicit Euler technique. Okay, because its another name is the Adam Bashford first order is exactly the explicit Euler technique, and this is the correct formula for it. Okay, so this is the yn plus one equal to yn plus h of f yn. This is the correct formula. Now the second order Adam Bashford technique, this is also an explicit technique, okay, and this is it is the correct formula for that, okay. So here A and B are the correct option. Here A and C are the correct option, okay, right. Now here this is an example problem. So now you need to solve this problem. So you have y prime equal to sine of y. So you need to use calculator to solve the problem. So first I will use explicit Euler technique and see what is the correct answer. So it says that yn plus 1 is equal to yn plus h f of xn yn. This is the explicit Euler technique, right? So here I need to find y1. Okay, let's just find y1. So I have not specified it, but let's find y1. So h is 0.05, y1 equal to y0 is 2 plus 0.05 into, this is my f of xy sine y into sine of y0, that is sine of 2. So what is the answer? Let me find it in calculator. So it is 2 plus 0.05 times sine of 2. So the answer is, from my calculator, I'm getting 2.04546. Okay, and dot 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 sum. Now I need to use the implicit Euler technique. Okay, now the formula is yn plus 1 equal to yn plus h of f yn plus 1. So that means here it will be y1 equal to y0 plus h of sine y1. So you cannot solve it straightforward. Okay, So we can do, we can define a function of f of y1 equal to y1 minus y0 minus sine y1, sorry, h sine y1. I can define a function like this, and I can use Newton-Raphson technique to solve the problem. So I need the answer y1, right? So the solution will be y1 at k plus 1. This is the k plus 1th time iteration in the Newton-Raphson, equal to y1 of k minus f of y1k divided by f prime of y1 k. Remember that here y naught is a constant, y naught is not a variable. Okay, y1 is the variable, so I will use Newton-Raphson technique on the y1, and similarly the function is defined on the based of y1. Okay, so just a moment. Right. So what will be the expression? The expression will be equal to y1 of k minus of y1 k plus 1 minus y0 minus h sine y1, sorry, it will be k only, y1 of k divided by 1 minus h cosine y1 of k. Okay, now you need a value of y1 of 0, so you can assume it as y0. Okay, that is 2. So your y1 of 1 will be equal to, if you do the calculation, you will find that y1 of 1 will come as 2.04453. Original, this give you 2.04546, and if you put y1 of 1 and you calculate y1 of 2, the calculation is simple, so I will just show you the final answer. You will find it will be 2.04449, and you will see that y13 will be similarly like 2.0444 to some other value. So it will, after one more iteration, it will simply converge. Okay, so this is the idea how to use explicit Euler and implicit Euler to solve this kind of problem. Okay. Now, yeah, which of the statement about the Adams-Moulton method is correct? This is the correct statement, right? It involves the terms at the next time step. Okay. Right. Now you need to use Euler's technique. This is the explicit Euler technique to solve the problem at x equal to 2.5. Okay. So first I will use explicit Euler technique. Then I can, this is analytically solvable. Then I can always compare the answer with the analytical solution. Then I will show that we are using analytical solution, we are getting exactly the same answer. So first do y1 equal to y0 plus h if x0 y0 equal to, now see that y0 is given at, so y0 equal to -1 and x0 equal to 2, right? Y2 equal to -1, that means x0 equal to 2, y0 equal to -1. So it will be -1 using a single step Euler. That means h will be 0.5 plus 0.5 into y0 minus 2, that means -1 minus 2, that is -3, divided by x plus 2, that means 2 plus 2 equal to 4. So if you do this, it will get -1 minus 3 by 8 equal to -11 by 8 equals to -1.375. So this is the answer. Now let me solve it using The analytical, so from the analytical solution, if you do the analytical solution, and I am writing it an analytical solution. Now, if you do analytical solution, the solution is very easy. You know that it will be some constant ln times c into x minus 2. Okay, the simple calculation. That means it will be y minus 2 equal to some constant c x plus 2. Now it is given at x equal to 2, y equal to minus 1. So it will be minus 3 equal to c times 4. This implies c equal to minus 3 by 4. So y equal to 2 minus 3 by 4 x plus 2. Now y at 2.5 equal to, now 2 minus 3 by 4 is 2 minus 3 by 2, that is half, minus 3 by 4 into 5 by 2 equal to minus 11 by 8. So it is minus 1.375. So the analytical solution is giving exactly the same answer like the this explicit Euler, single step explicit Euler technique. Alright. Now let's go to the second problem. The similar kind of thing we need to use. That is, the problem is dy dx. So I need to write it in this form, f of xy, and f of xy equal to y square plus x. Now here it is y0 equal to 1 and x0 equal to 0. So here h is equal to 1 and I need to use y2. That means it will be a two-step explicit Euler technique. So the first step will give me y1 equal to y0 plus h, y0 square plus x0. So this is the first step. This is equal to 1 plus 1 into 1 is equal to 2. Now at the next step, I need to find x1. x1 equal to x0 plus h equal to 1. So y2 will be y1 times h time y1 square plus x1. It will be 2 plus 1 into 2 square plus 1 equal to 2 plus 5 equal to 7. So this is the correct answer. Right. Now, so I have already solved similar this type of problem. Okay. So this is another example. This is from the last year assignment question. Okay. Moment. So here it is told that this is true for any constant or any straight line. Okay. And you need to find the value of these two constants, that is c0 and c1. So how to do that? So first assume that fx equal to x, because this is true for any straight line. You can take x plus b, cx plus d. I am taking the simplest one, that fx equal to x. Okay. So 0 to 1 x dx equal to half equal to c0 into f of 0, that is 0, plus c1 into 1 f of 1, that is 1 c1. So c1 equal to half. And now it is true for any constant. Again, I am taking the simplest case, 0 to 1, 1 of dx equal to 1 equal to c0 times 1 plus c1 times 1. Now c1 is already half, so c0 equal to half. So c0 c1 is half and half. So this is your correct answer. Okay. So this is for straight line. This is for constant. So I hope the idea is clear. This is very easy. Okay. So finally we will get that this is the correct answer. Okay. Okay. So now this is a this is some different type of problem. This is from the here I will tell you about two ideas. Okay. Now all the so suppose you are solving a differential equation. Now see the Euler explicit form. It is dy dx equal to f of xy. You can only solve this in this manner. Now suppose if you have a form of a function like d2y dx squared equal to some, I don't know, g of xy. Okay, how will you use Euler explicit method? Okay, so this is the idea. So here you can define another variable z equal to dy dx, and dz dx is equal to g. Okay, so you will have d dx of y z equal to z and g, and for this is a vector form, and for this expression, for this form you can use explicit Euler. Okay, so here this idea will be used lightly, but this is a completely different problem. So so this problem says that you have a differential equation d2y dx square plus 6 by x dy dx plus qxy, where qx is unknown to you. It is some continuous function in 1 and 3. If the Wronskian of y1x and y2x. Now what is Wronskian? I will tell you the definition. W equal to y1 y2 prime. So x, this is y1 x y2 x, okay, minus y2 y1 prime. This is the definition of Wronskian. Okay, I'm not going into the details what is Wronskian. Okay, but it actually tells you how many independent solution your differential equation have. So it says that y1 y2 y2x both are the solution. Okay, so it has the Wronskian. So this is the value of the Wronskian. Okay, now this value of the Wronskian at x equal to 1 is 1. Then you need to find what will be the value of Wronskian at x equal to 2 from this differential equation. Okay, now let's do that. So the function is y double prime. So it is d2y dx square. I am writing a shorthand notation y double prime plus 6 by x y prime plus qx y. I think this is homogeneous. Yeah, equal to 0. Right. Now the Wronskian. So that means implies y1 double prime plus 6 by x y1 prime plus q of x y1 equal to 0, because y1 is a solution. That means it must satisfy this governing equation, and y2 double prime plus 6 by x y2 prime plus q of x y2. That y2 is also a solution. Okay, now the Wronskian is w y1 y2 prime minus y2 y1 prime. Let me find dw dx. It will be y1 y2 double prime minus y2 y1 double prime. There will be y1 prime y2 prime minus y1 prime y2 prime y1 prime, so they both cancel each other. Okay, finally I will be left with this. Now I can substitute y1 double prime and y2 double prime from these two equations, equal to y1 minus 6 by x y1 prime minus q of x y1, sorry, 6 by x y2 prime minus q of x y2 minus y2 minus 6 by x y1 prime minus q of x y1. So this term cancels each other, and finally I will be left with 6 by x y2 y1 prime minus y1 y2 prime. So this is minus 6 by x into w. Okay, because w is y1 y2 prime minus y2 y1 prime. So I get dw dx equal to minus 6 by x w. That means if you take the logarithm and do those steps, you will get w equal to c by x to the power 6, where c is a constant. Okay, after integration. Okay, I'm not showing the step because this is very easy. Now at x equal to, I don't have space here, I am at x equal to 1, w equal to 1, so c equal to 1. Okay, it is given it is given. Now what will, so answer the question is what will be its value at x equal to 2. So at x equal to 2, w will be equal to 1 by 2 to the power 6. So this is the answer. So this is your correct answer, 1 by 2 to the power 6. Okay, I hope this is clear. You just need to find dw dx and other things will be very easy to you. Right. Now this is another example. So Simpson's one-third rule is applied on this with subinterval h equal to 1. Okay, will give, there are four options. Now in the last class I have already told that Simpson's rule is based on a quadratic polynomial, so it will give you the exact answer. Okay, so this is with it will give you the exact result. But here you have two subintervals, -1 to 1, -1 to 0 to 1. Okay, this is one subinterval, this is another subinterval. I will just show you for a single. Okay, so I don't have much time today, but in the last class I have solved a similar kind of problem. Okay, where you can verify using the Simpson's rule with h equal to 1, it will give you the exact result. Okay, and then the last class I have solved exactly the same similar problem, so I am not showing it again. It is this, you can treat it as HW and verify it. Okay. Okay, now this is another problem. So I will solve this problem. So it says that dy dx equal to 1 plus y square, and here, so it will be again two step Euler equation. Okay, so the first will be equal to, so y1 equal to y0 plus h into 1 plus y0 square. So it will be equal to, so y0 is 0, h is 0.2 into 1 plus 0. So the result will be 0.2. Now you need to find y0, y of 0.4, that means y2 equal to y1 plus h into 1 plus y1 square. That means 0.2 plus 0.2 into 1 plus 0.2 square. You will find this answer will give you 0.408. So this is your correct answer. Okay, right. So this is a simple example. Okay, but I wanted to show you in the Matlab as well. So I have provided it. So this function is odd function, and you can see from the limit that this will cancel each other. So I will be just left with 4 times into 2 into 0 to 5 pi by 2 cos x dx. Okay, and you can find the answer very easily. Just do it. Okay, now I wanted to show you in Matlab because I haven't tested it. Let's see if Matlab work on this function, right? So let's verify it. So I will just use the symbolic toolbox because we already know that for the uh, integral and the trap z it will work. Then just check the int function, int comment for this function. Okay, just a moment. It is taking some time. Okay, so my Matlab is taking some time. So in that case, let me. Okay, yeah. So now my Matlab is open. 1 second. Let me share my screen. Okay. So the function was, so first I need to define a symbol x if equal to exp pi star x cube star sine x cube plus 4 times cos of x. If minus 5 pi do, that is minus star pi. So let me just check the answer. Oh, so this is a mistake. Oh, so it is giving, so I need to convert it to double. Oh, no, it is not giving the answer. Okay, so yeah, so you can see that for this Matlab is not giving an answer. Okay, so I have made a mistake. It is pi x square. Okay, I hope it will not work. Okay, e to the power pi x square times sine x cube plus 4 times cos x. So you can see that for this function. Okay, so I just wanted to check if it works, and it does not. But if you do symbolic computation, you can try it yourself. I am pretty sure that it will give you the correct answer. All right. Uh, okay. Okay. You can try with the you can try with the numerical computation. And okay, let me just verify if it works for the numerical computation. So, oh, just, uh, I do not want to remove this. Just f equal to at the rate x xp pi times x square into sine x cube plus 4 times cos x. So I will just, I don't need double. It will be integral f comma minus 4 pi. Let's see if it can give some answer. Oh, okay, sorry. So I need to provide dot dot. No, Matlab is giving garbage answer for this because it uh, we analytically know that this from minus 5 by 2 to 5 pi by 2, this term will finally get cancelled each other, but MATLAB doesn't know that, so it is generating some garbage value because 5 pi 5 2.5 pi to the power square is giving a very large answer. Okay, so finally it is giving me a garbage value. Okay, so MATLAB is not working for this kind of function. So this is one example where both the analytical and the numerical thing fails. Okay, so I will stop sharing the screen, and then now I can go back to my tab once again. I have two problems left. Right. So for this problem again, okay, so yeah, so you can say this. I need to, so you need to find the correct answer using the explicit Euler technique. Okay. Right. So I need to find out y 0 point at 0.5 and the step size is 0.25. So two step Euler. So I will just quickly write a first step. So y1 equal to y0 plus 0.25 into 2 cos into that thing. So, and this is 0. So it will give me 2 minus y0. Finally, you will get the answer to be 1.25. Okay, just verify. This is a very straightforward calculation. Then you need to find y2. Y2 will be equal to y1 plus 0.25 times 2 into cos into 4 pi x1 by 3, and x1 is 0.25. So 4 pi by 3 into 1 by 4 minus 1.25. Okay, so it will be 1.25 plus 1 by 4. 2 cos pi by 3 is 1 minus 1.25, and you will finally get the answer 1.1875. Very straightforward calculation, and this will be your correct answer. Okay, and now this is the last problem. This is also another theoretical problem, not from the analytical, not from the numerical. You do not need to do numerical computation over here. Very straightforward question. So here it is given that dy dx plus 2xy equal to y, and you need to find the value limit extends to infinity of yx. It is given that y0 equal to 0. So I need to find the if, okay, the integrating factor, and if will be e to the power integration 2x dx. You all know these things. Okay, this is just a very simple problem. So e to the power x square. So I need to multiply the integrating factor on the both side. So it will be e to the power x square dy dx plus 2xy e to the power x square equal to y e to the power x square. So this implies plus 2xy equal to x, not y, sorry, x. That means d dx of y e to the power x square x e to the power x square. That means y e to the power x square. So if you integrate, if you take dx on the right hand side and integrate it, it will get half of e to the power x square plus some constant c. This implies y equal to half the c into e to the power minus of x square. Now it is given that y of 0 equal to 0, but you don't need that actually, because if you directly put limit x tends to infinity y equal to limit x tends to infinity half plus c into e to the power minus x square. So this c is associated with e to the power minus x square. Now if x tends to infinity, this term will vanish, simply 0. So you will left with half. So the correct answer is limit x tends to infinity y of x is equal to half. Okay. So this is the last problem that I have solved today. So I hope all the things that I have told is the ideas are clear. I will share all the codes that I have told today, that I have taught today, and in the next class Sunday I will again first continue with code. I have planned to show you the inbuilt ODE solver that is available in Matlab, and we will solve many problems regarding that. And I will again solve some theory problem which is required for your assignments. So good night for today, and we will meet on Sunday. Thank you.